Hello, everybody. When we were doing our practice test, there were probably the most questions about these induction style problems. So I thought I would just knock them all out in one video. So we got 14, 15, and 16. A lot of induction problems on last year's test, so must be important. So the first one here says that if n is greater than 2, meaning that our base case is going to be n equals 3, because that's the first integer past 2. So then we check what 2 to the third is, and that equals 8. Last time I checked, 8 was greater than 6, and 6 is equal to 2 times 3. So we proved that there is at least one number for which our conjecture is true. Then we assume that there is some number where 2 to the n is greater than 2n. We're allowed to do that assumption because we proved that there exists at least one number for which the conjecture is true. So what we do is we consider the n plus 1th case. So we consider 2 raised to the n plus 1, which is the same as 2 times 2 to the n. There's a couple different ways you can proceed. One way to do that is to say, well, that's equal to 2 to the n plus 2 to the n, right? That's what 2 times 2 to the n means. And then I'm going to use my induction hypothesis. You always have to use your induction hypothesis. So I'm going to use this right here and right here. I know that each of those 2 to the n's is greater than a 2n. I also know that 2n is greater than 2. I know that this right here is greater than 2 because n is greater than 2. And so I can write that this is greater than 2n plus 2, which is equal to 2 times n plus 1. So we proved that the n plus 1th power is greater than the n plus 1 multiplication, 2 times n plus 1. And that means that the proof is done. By induction, it is done. We proved it was true for at least one value, and then we showed that if it is true for a particular value, it also implies that it's true for the next value. There's a couple other ways you could have shown these steps right in here. I just thought this was a nice, clean way of using the induction hypothesis twice for each of the 2 raised to the n powers. All right, let's slide on down and let's do number 15. Okay, remember, how do we slide? That's how we slide. Okay, show by induction that this equals that. First is n equals 1. That means that we just have one odd number on the left side, one squared on the right side. Check. Then we assume the orange stuff. This is my orange stuff. I'm just going to shorthand it. I would like you to actually write it all out on the test, but I'm going to assume that that is true. And then I consider the n plus 1th term. So 1 plus 3 plus 5 plus ... 2n minus 1. And then the next term, I'm okay with you writing 2n plus 1, or you can write like this, 2 times n plus 1 minus 1, because that is maybe a little more explicitly showing the n plus 1th term. What we have here is star. This is orange star. So we can replace it with our induction hypothesis that this equals n squared. This is our n plus 1th term, so let's just distribute it out. Let's just combine our like terms, and let's factor that as n plus 1 times n plus 1. We just proved it by induction. We showed that it was true for a particular value of n. We assumed it was true for that value of n, and proved that it implies that the next value must also be true. Therefore, it is true for all n greater than or equal to 1, because we started at 1. Last one, number 16. A lot of people got tripped up by just sort of the notation here. Let's set n equal 1 first. Don't write r equals 1, write n equals 1. So what that means is we have the sum from r equals 1 to 1 of r times r factorial, which is really just a single term, 1 times 1 factorial, which is just equal to 1. The right side of the problem is 1 plus 1 factorial minus 1, which is also equal to 1, because this is 2 minus 1. So it checks out for the base case. And then we're going to do the same thing. I'm not going to write it out, but I want you to write it out on the test. I'm going to assume star is true. Pretty star. So then I'm going to consider the n plus 1th term, r equals 1 to n plus 1 of r times r factorial. Well, what that equals is it equals the first n terms plus the next term, where n plus 1 is the value of r. The first part is orange star. That's a better star, maybe. So I can replace that with n plus 1 factorial minus 1. The rest of it is n plus 1 times n plus 1 factorial. Take a second. What do they have in common? They have this pink business in common. And the pink business is n plus 1 factorial. So I factor that out. The first term had a 1. The second term had an n plus 1. Now, you might be wondering, I hope you're wondering, what the heck did I do with this negative 1? The answer is I did nothing with it. So I just am going to write it down. I couldn't factor it out because it wasn't attached to the common term of n plus 1 factorial. So now we're sitting at n plus 1 factorial, and here we've got n plus 2, and here we've got minus 1. And that's great, because n plus 1 factorial times n plus 2 is n plus 2 factorial minus 1. Check. Boom, boom, boom. That's what we wanted to prove, because that is the next term on the right-hand side of our conjecture. So there you go. 3 more examples of induction. Please let me know if there's anything else you need. Happy studying. Make sure to smash that subscribe button.